Hey everybody. So I wanted to make a quick video that goes over quantum numbers. We will talk about this in class, or we already did talk about this in class depending on when you're watching the video. But I know it's also one of those parts that really confuses people. So I wanted to take some time and make another resource for you to use. The main thing to remember about quantum numbers is that they are there to simplify our lives. If you remember, we originally started talking about the Schrodinger equation. We said we've got some function psi of x that's being operated on that's going to give us some energy psi of x. And that alone was confusing enough, right? This takes understanding the existence of the electron to be in terms of some function instead of just some position. And then the Hamiltonian is going to be some amount of energy, kinetic and potential. And the way we kind of simplified this was to say, look, rather than thinking about all of this, we're just going to say that we get some answers. And we're going to get like the first answer, we're going to get the second answer, we're going to get the third answer. These answers are going to have relatively complicated mathematical functions to them. And so what quantum numbers do is they give us a way to refer to these different answers and gives us some structure for how the answers relate to each other. But probably the better reason to look at quantum numbers is because there's actually not just three answers, there's actually an infinite number of possible answers. So quantum numbers give us a way to kind of refer to these answers and the ways that they relate to each other. So let's go ahead and get into it. We've already started talking about the first quantum number, even though I didn't entirely mention that we were talking about a quantum number. That is going to be the number n, which is referred to as the principal quantum number. I'm going to use Q hashtag for quantum number, or Q pound sign for you older folk. So we're going to use quantum numbers. This is referred to as the principal quantum number. It has important implications on the energy for the ways that the quantum numbers are going to relate to information about those functions, the radius, and that's really going to be the two main things it refers to. We're also going to have certain values that are allowed to be n. That's going to be 1, 2, 3, 4, all the way up to an infinite number of solutions. In chemistry, we're typically only going to work with the first 6 or 7 n values, but theoretically it goes on forever. You'll notice that because these are referring to functions, we have discrete values. We have like the first answer, the second answer, the third answer, so on. But underneath these answers, there's actually other aspects to them. This one doesn't represent just one answer, it represents multiple possible answers that all kind of fit inside there. So that gets us to getting more defined in terms of which function we're talking about is going to be our L value, which is referred to as the angular quantum number. This one is going to be a slight impact on energy. It's going to have a slight impact on radius, but it's going to tell a lot about the shape of the orbital that we're looking at. So each of these orbitals, each of these mathematical functions we're representing with these values is going to have a particular shape associated with it, and that's going to tell us about where the electron is, and this L value is going to tell us a lot about that shape. This has values starting at 0 for the lowest shape. Oh, actually, let's write this. And they can theoretically go on forever, just like the other set. But this being a number that's below the principal number is going to be restricted by the principal number to a maximum of n minus 1. And we'll talk about how we can implement those limitations after we get through all of the quantum numbers. The last, which is going to be a subset underneath this last one, is going to be the m sub L value. This is referred to as the magnetic quantum number. And this one is actually not going to affect energy unless we apply a magnetic field, which we're not going to do this quarter. It's not going to impact radius. And more than it's going to impact the shape, it's going to be the orientation of the shape. So for example, I can point the pen up, that would be like one orientation, or I can point it down, that would be like another orientation. And this m sub L is really going to be how is the shape determined by L oriented. And because it has those multiple orientations, it's going to have values of negative L all the way up to L, all the way up to positive L. Depending on the orientation, depending on how complicated the shape is, we've got a lot of different possible orientations associated with it. So when we look at this, it may seem a bit daunting, but really what we're doing is we're trying to make our lives more simple. If we were just looking at the mathematical functions and the infinite number of mathematical functions, it's really hard to tease out the physical meaning. And with just these definitions, it's hard to get that practical application. So we really need to start looking at what these numbers refer to in terms of their energy, the radius, the shape. But before we do, I want to mention two more things. We've got a special number, which is the electron spin number. And this is going to have values of minus a half or plus a half. Those are the only two choices for the electron spin number. And the way to think about this in terms of how we group these together, I've been referring to them as sets of answers. You'll notice everything is, besides the special electron spin, everything is integer values by steps of 1. And even the electron spin is still a step of 1, but everything's integer values. And I've been referring to these as sets, but because it's quantum mechanics and chemistry and has very specific meaning, we give special terms for all of these. So the n value gets referred to as the shell. So if we just had the n value, we'd be looking at what shell of the atom we're looking at. If we had the n and the L value, we'd be looking at the subshell. Right, we'd be looking at what do we know about the broader idea, what do we know about the more specific ideas. And if we had all three of these, the n, the L, and the m sub L, this would be the orbital. That would define a particular orbital having all three quantum numbers. The m sub s, this one is really looking at the electron. So interestingly, we can look at these three as being in reference to the atom and the space around the atom, and this one being in reference to the electron that's interacting with the atom. I like to think about it in terms of an analogy as n, L, and m sub L are the address to a house. You've got the city, the street, and then the house on the street, right? So that gives us more specification. Inside the house, we can have a certain number of electrons. It turns out it's a duplex, so you either got living in the front unit or living in the back unit, right? The plus a half or the minus a half case. So by having all four of these, we're specifying an individual living in one place, versus these three, the shell, subshell, orbital, just define where the place is. Now this means as we go through it, we've got a different amount depending on how well we specify our information. We're going to have a different number of electrons that are able to exist in that space. Keeping in mind when I say space, I'm meaning like coordinate space, not necessarily physical space. How these relate to physical space is kind of interesting, and we can start to look at that by looking at the common trends we have across the numbers. So let's start to look at that. I'm going to start with really looking at the shapes, because I feel like having a more visual representation gives us a good idea gives us a better idea that we're really just looking at a mathematical function. And we'll do that while we also look at how the numbers are restricted. So we're going to start with the n equals 1 case. Now, based off of the rules that you hopefully wrote down or that you're refreshing on, if n equals 1, the only possible L value is n minus 1, which is 0. And the only m sub L value that is possible is L plus or minus, positive L to negative L would also be 0. Based off of this, we're looking at this first shell, and this is going to be the entirety of the first shell. This refers to some function. It's not just x, it's going to be all 3 components, x, y, z coordinate space. And if we plotted this in 3-dimensional space, forgive me, I can't actually draw too well in 3-dimensional space, but you would get something that just looks like a circle, right? So if we took this function and we made a 3-dimensional plot of it, we'd get something that would have a spherical shape, except it wouldn't be uniform across the entire space. You'd have an area where you have high probability, and you'd have an area where you have lower probability. It would be circular, like I'm trying to represent, but you'd have areas of high probability and low probability. In order to split these ideas up, we usually show this as 2 separate plots. One plot for the shape and one plot for the radius. So rather than trying to do that density plot over the top, we often will show it as one plot for the shape, really defined by this L value, and then one plot for the radius. This is going to be radius versus probability. It's going to look something like that. So here, at this value, we're going to have a really high probability. That's really off center. Wow. We're going to have really high probability at this value, and then it's going to taper off. Notice in this situation, we don't end up with just one possible radius. We end up with a likelihood of radius, with one being most likely, but a lot of different possibilities. And they're all going to follow this shape of being kind of spherical, where as you go out from this, you're going to have some place where you get more likely and then less likely. But it's not going to be uniform. It's not going to be just around that circle. Let's go ahead and look at another one of the shapes. And this one gets a little bit weird. But we're going to look at the second case. And if n equals 2. Now in this case, we actually have a lot of possibilities. In the n equals 2 shell, we can have L equals 1, or we can have L equals 0. Now we already did an L equals 0. The nice thing, again, the quantum numbers group together in this way that gives us information. The L equals 0 is going to have the same shape that we saw before, but the radius and the energy is going to be different because we've got this n equals 2 value. But the shape is going to be the same. So that L value, for all L equals 0, we get that spherical shape. Let's go ahead and look at the L equals 1. In this case, the L equals 1, we can have m sub L equal minus 1, 0, or 1. For the L equals 0 that we're not going to look at, you're going to only have m sub L equals 0. Same thing we saw before. The shape, again, these numbers, depending on which ones we pick, are going to define the shape and then the orientation of that shape. And it's going to define some function in 3-dimensional space. Now this one gets a kind of interesting shape, but you end up with this thing that in my opinion, looks like two balloons attached to each other. Some people say it looks like a dumbbell, but it really looks like two balloons attached to each other. Now, if this is oriented along the z-axis, we'd say that this would be the 0 orientation. And then depending on whether it's the x-axis or y-axis, we'd have some different orientation. That would be specifying the m sub l value, gives us that orientation. Is it pointing up? Is it pointing sideways? Is it pointing into the board? But all of the L values, all of the L equals 1 values are going to have this type of shape, and then just the orientation changes. Again, the radial information is going to look similar, but it's going to be slightly different. For the n equals 2, L equals 1 case, we're going to have something that looks it's a little bit broader, a little bit further out, and actually doesn't go quite as high. Again, this is radius, this is probability. And there are lots of different probabilities we can look at. If you look at the n equals 2, L equals 0 case, we actually get a different radial probability. But I don't want to get caught up too much in that right now. I just want to make sure that we get this idea that the quantum numbers specify a function, which then gives us physical information about the system. And they simplify our representations because we're going to have this nice kind of correlation of anytime we've got L equals 0, we've got the same shape. Anytime we've got L equals 1, we've got the same shape. Anytime we've got the n values, that's going to give us most of the information about the radius or about the energy. So, the essential skills that we need to be working on is how many electrons fit, what physical information can we get, and is it a valid set? This last one is actually the first one. Is it a valid set? That really is just asking, does it follow the numbers that restrict us? Let's just pick a random set of numbers and see if we can figure it out. So I'm going to try, let's try something weird. N equals 8. This is outside of what we usually do in chemistry because we're a little bit high. N equals 8. L equals 5. M sub L equals question mark. What are the possible M sub L values in this case? And how many electrons could you specify with those M sub L's? I'm pausing so you can work on it. Don't just wait for me to give the answer. In fact, you should pause the video if you're just waiting for the answer. Try to figure it out. So, if you had to rewind the video and look at the rules, or if you're looking in a textbook, we know that the M sub L, the thing I wrote down was it goes from minus L up to positive L. It doesn't have anything to do with N, right? N specified what L's are allowed, and then our L specifies which M sub L's are allowed. So in this M sub L case, we have 5, 10, 11 possibilities. We can be -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Holy moly, that's a lot. And for each of these M sub L's, we can have, so those would all be valid choices. If n equals 8 and L equals 5, notice this gives us our subshell designation. For n equals 8 and L equals 5, we'd end up with 11 possible orbitals that would all be valid. In each of those orbitals, we can either have a person, an electron, in the front unit or in the back unit of the duplex. So for each of these orbitals, we can fit 2 electrons, and I'm not going to write them all down, but that's going to be the same way the whole way through. So we can figure out how many electrons fit in any of these valid sets. In any of these valid sets, we'd have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. So with n equals 8, L equals 5, we'd have 22 possible electron sets. If we specified more, if instead of just saying n equals 8, L equals 5, if we said n equals 8, L equals 5, and we just pick one of our, pick your favorite number. I'm going to pick m sub L equals 3. This orbital could have 2 electrons. Right? Notice I've got more specification. I specified all 3 quantum numbers, so you could have 2 electrons fill that. Or you could go even further, and you could have n equals 8, L equals 5, m sub L equals 3, m sub S equals plus 1/2. And this would be specifying a single electron. So having all 4 quantum numbers, the 3 orbital numbers and the electron number, combined to give us the information about a single electron. We can use that information to figure out is it a valid set or not, how many electrons fit, and we can also get into the kind of physical information. But the physical information is really something that kind of goes beyond what I wanted to do in this video. I just wanted to make sure that we understood how we could write down the quantum numbers, this idea of shells, subshells, orbitals. And I'm also going to show you one more thing that should allow you to write these subshell designations a little bit easier. And that is the definition. And it really is just a definition. It comes from historical context. But L equals 0, we call S. L equals 1, we call P. And L equals 2, we call D. These, since the L values are the major distinguisher of the shapes, these correspond to different shapes. The SP and the D correspond to different shapes. And it's really just in chemistry where we get this kind of designation. So if we had something that was, going back to that first case, n equals 1, L equals 0, m sub L equals 0, this would be a 1s subshell with only one option, with only one m sub L. If we wanted to designate the orbitals or represent the orbitals, we could draw this as one box. That's called a 1s. If instead we wanted to do n equals, let's do n equals 3, L equals 1, m sub L equals -1, 0, or 1, this would be our 3p subshell. And because I've got 3 possibilities, I would draw 3 boxes. The -1, the 0, and the 1. To represent my 3 orbitals associated with this subshell. Hopefully that gives you enough to start writing out subshells, and kind of thinking about how we can do pictorial representations of the places where electrons could be.